Hello, welcome to EPG Pathshala Biophysics, Paper 2, Quantum Biophysics. I am Angshuman Lahiri, Associate Professor, Department of Biophysics, Molecular Biology and Bioinformatics, University of Calcutta. In this paper today, we are going to take up Module 15 dealing with the extended Huckel method and the need for self-consistent field theories. We have already discussed in the previous modules methods applicable to molecules in which the electrons could be divided into pi electrons belonging to atoms other than hydrogen and other electrons. This constituted a restriction on the class of molecules that could be studied with this method. It appeared that the systems studied by these methods belong to the class of conjugated hydrocarbons and their derivatives. In this module, we shall introduce an approximation known as the extended Huckel theory that divides the electrons into two groups. One, the valence electrons of the atoms constituting the molecule, and two, the 1s core electrons of these atoms. Naturally, the 1s electrons of hydrogen atoms are valence electrons, so they belong to the group of valence electrons. This mode of division is applicable to describe some particular aspects of the electronic structure of any type of molecule. In this module, our objectives are to introduce the main features of the extended Huckel theory, to introduce the population analysis tool proposed by Mulliken, to discuss some application of extended Huckel theory in biophysics, to discuss the need for self-consistent field molecular orbital theories. Although the idea for extended Huckel theory have been proposed by some other scientists, a systematic development of the extended Huckel method was made by Roald Hoffmann in 1963 and subsequent years. Roald Hoffmann is an American scientist who was born in 1937 and he got the Nobel Prize in Chemistry in 1981. The extended Huckel method he proposed is similar to the Huckel molecular orbital method for conjugated hydrocarbons, but it is applicable to virtually any molecule irrespective of whether it is conjugated or not. Before going to the extended Huckel theory proper, let us briefly recapitulate the basic steps of the simple Huckel molecular orbital theory. In the Huckel molecular orbital theory, we suppose that in our system, we can treat separately the pi electrons from the sigma electrons. And then we set up a basis of the pz orbitals, one for each atom donating a pi electron. And then we seek molecular orbitals that are linear combinations of these pi electronic atomic orbitals that minimize the energy of the system. We have already seen how to construct such molecular orbitals. For example, in this equation, the big psi, that is the molecular orbital, is written as a linear combination of the small psi's, psi 1, psi 2, psi 3 up to psi n, which are the atomic orbitals. And this is written as C1 psi 1 plus C2 psi 2 plus up to Cn psi n. That is sum over I equals 1 to n Ci psi I. This equation involves the coefficient C1, C2, C3 and so on, and any arbitrary coefficient Cr need to be determined from a minimization condition. And what is the minimization condition? Consider the energy of the molecular orbital. And this energy has to be written as psi h psi divided by psi psi. That is, in the numerator we have the matrix element of the Hamiltonian involving the wave function molecular orbital psi, and in the denominator we have the overlap integral of the molecular orbital. We seek the coefficients in such a way that the energy is optimized, and this can be achieved by making the first derivative with respect to the coefficients all vanish. That means we require that del E del Cr equals 0. And a simple calculation that we have carried out in the previous module shows that this leads to the matrix equation sum over R H SR minus E S SR Cr equals 0. Now in the Huckel approximation, the overlap matrix elements S RS equals 1 only if R equals S, otherwise it is taken as 0. And for an all carbon system, we take all the diagonal elements of the Hamiltonian matrix to be equal to a parameter alpha, that is HII equals alpha, and the off-diagonal elements between the nearest neighbor orbitals are set to a parameter beta, and all others are set to 0. Since the matrix equation that we constructed will have non-trivial solution if the determinant is 0, that means we have determinant of H minus epsilon S, or determinant H minus ES equals 0. This will give us a polynomial equation in E of degree n, where n is the number of atomic orbitals used to construct a molecular orbital. Since such polynomials will have exactly n solutions, there will be n molecular orbitals or sets of coefficients CRI with energies EI. The major procedural difference between the Huckel molecular orbital method and the extended Huckel theory lies in the way the electrons are partitioned. The Huckel molecular orbital method partitions the electrons into two groups, one being the pi electrons, and the other group contains all other electrons called the sigma core. The group of pi electrons only is considered explicitly in the case of Huckel molecular orbital method. The rest of the electronic contribution in this method is incorporated parametrically. The extended Huckel theory, on the other hand, puts the valence shell electrons into one group and the inner shell non-bonding electrons are put into another group. This method treats the electrons in the first group explicitly and parameterizes the effects of the rest. The extended Huckel procedure allows us to calculate the basic properties of all organic systems, aliphatic and aromatic, as well as inorganic structures with one simple parameterization. The calculation starts with the expansion of a molecular orbital in terms of a linear combination of atomic orbitals, the LCAO-MO approach. As we have seen in the previous modules, application of the variational method leads to the equations sum over I to n Hij minus E Sij Cij equals 0, j equals 1 to n. In this equation, Cij are the expansion coefficients for the molecular orbitals in terms of the atomic orbitals or the basis functions. The Sij elements correspond to the overlap between the ith and jth basis functions. The Hij elements are the Hamiltonian matrix elements and E the total energy. The overlap integrals can be calculated once basis functions are chosen and the molecular geometry fixed. In his original work, Roald Hoffmann chose a basis set of m hydrogen Slater orbitals exponent 1.0 and n 2s and 3n 2p carbon Slater orbitals exponent 1.625 for a hydrocarbon of the type CnHm. The order of the resulting secular determinant should therefore be 4n plus m. Since overlap integrals are not neglected, all off-diagonal energies are retained. The critical element of the theory is the choice of the Hamiltonian matrix elements. The extended Huckel theory parameters. Here, the diagonal elements HII are equated to the valence state ionization energies of the particular atoms. Hoffmann suggested the following values for saturated and unsaturated hydrocarbons. For example, HII equals minus 11.4 electron volt for 2p atomic orbitals of carbon, HII equals minus 21.4 electron volt for 2s atomic orbitals of carbon, HII equals minus 13.6 electron volt for 1s atomic orbitals of hydrogen. The off-diagonal elements Hij are obtained as Hij equals 0.5 K into HII plus HJJ Sij, where HII and HJJ are the diagonal elements of the Hamiltonian matrix and Sij are the overlap elements for ith and jth orbitals. This parameterization was first discussed by Mulliken and was later used by Wolfsberg and Helmholtz. Hoffmann suggested the value of K equals 1.75 from detailed considerations of theory and experiments. Although the extended Huckel theory is conceptually simple, one needs computer programs for evaluation of the matrix elements and diagonalizations. The input to such a program includes the precise coordinates of the various atoms. The overlap matrix is then computed and the Hamiltonian matrix is then constructed from it using the parameterization schemes. The complete set of equations is solved by two matrix diagonalizations, which are the most time-consuming steps in the entire calculation. The resulting energy levels and wave functions can then be analyzed. A freely available program for extended Hückel calculation is called yet another extended Huckel molecular orbital package. This can be used for calculation and visualization. The package features a program bind that performs the extended Huckel calculations on isolated molecular systems and extended systems in 1, 2, or 3 dimensions. Let us now discuss the analysis tool suggested by Mulliken, which is known as Mulliken populations. The electron densities and bond orders that could be calculated from the simple Huckel molecular orbital method provided a useful conceptual framework for relating the theory to experimentally observed molecular properties. For example, bond lengths or electron spin resonance splittings. Are there analogous quantities to describe the distribution of electrons in an all-valence electron method, such as the extended Huckel theory? A number of such measures have been proposed, and one of the most popular and widely used such quantities is the one that was proposed by Mulliken. Let us take a real normalized molecular orbital phi I from two normalized atomic orbitals chi j and chi k. So phi I equals Cji chi j plus Cki chi k. The square of this molecular orbital will tell us about the electron distribution. So phi I square equals Cji square chi j square plus Cki square chi k square plus 2 Cji Cki chi j chi k. If we now integrate over the electronic coordinates, because of the normalization condition of the molecular orbital and the atomic orbitals, we will get 1 equals Cji square plus Cki square plus 2 Cji Cki Sjk, where Sjk is the overlap integral between the atomic orbitals chi j and chi k. Mulliken proposed a conceptual division in which one electron in the molecular orbital phi I contributes Cji square to the net atomic orbital population of chi j, Cki square to the population of chi k, and 2 Cji Cki Sjk to the overlap population between chi j and chi k. For 2 electrons in the molecular orbital, these figures should be doubled. We now designate the net atomic orbital population of chi j due to 1 electron in the molecular orbital phi j by Qji and the overlap population between chi j and chi k by pjki. Then qji equals cji square and pjki equals 2cji cki sjk. The Mulliken net atomic orbital population qji for each atomic orbital chi j and the Mulliken overlap population pjki for each distinct atomic orbital pair chi j and chi k will then be obtained by summing over all the electrons present in the molecular model. So Qj equals sum over I going over all the molecular orbitals Ni Cji square, which is identical to sum over Ni Qji, and Pjk equals 2 into sum over all the molecular orbitals Ni Cji Cki Sjk, which is identical to the sum over Ni Pjki. The sum of all the net atomic orbital and the overlap populations will be equal to the total number of electrons in our molecular model. That is, all the valence electrons for the extended Huckel method. Let us now discuss the extended Huckel energies and their relation with Mulliken populations. The orbital energy of a real molecular orbital phi I can be written as EI equals sum over all the atomic orbitals Cji square Hjj plus 2 j less than k sum over all the atomic orbitals Cji, Cki, k, sjk, hjj plus hkk divided by 2. The first term comes from the contributions to the net atomic orbital population, and the second term comes from the overlap population. We can rewrite the previous equation as EI equals sum over all the atomic orbitals Qji Hjj plus sum over j less than k jk running over all the atomic orbitals Pjki k Hjj plus hkk divided by 2. From the last equation, one can see that the energy of an extended Huckel molecular orbital comes from the net AO populations and overlap populations weighted by the respective energy weighting factors. By summing over all molecular orbitals times the occupation numbers, the total energy can be written as E equals sum over j running over all atomic orbitals Qj Hjj plus j less than k jk running over all the atomic orbitals Pjk into k into Hjj plus hkk divided by 2. These equations allow us to understand how the electron distribution contributes to the computed energies. This becomes very useful when we try to understand the energy changes which occur as molecules are stretched, bent or twisted. Although the extended Huckel theory was an improvement over the Huckel molecular orbital method, it had its own drawbacks. The extended Huckel theory has now been largely superseded by more sophisticated other semi-empirical and ab initio molecular orbital methods. The main deficiencies of the extended Huckel method is that potential energy surfaces are poorly reproduced. The method is restricted to systems for which experimental geometries are available, and the method is now primarily used on large systems such as extended solids for band structure calculations. Although the extended Huckel method suffers from some drawbacks, there are some advantages also. As we mentioned earlier, extended Huckel calculations cannot be used blindly for optimizing the structure of a system. Although modern-day ab initio quantum chemical methods are quite reliable for that purpose. On the other hand, if we know the geometry of the molecules, a number of studies over the years have shown the usefulness of extended Huckel calculations for such systems. Since the extended Huckel theory does not take into account the electron-electron interaction explicitly, the energy levels and orbitals generated by such calculations for a system do not depend on the number of electrons in the system. So the relative energies of different electronic states calculated by the extended Huckel method will not be very accurate quantitatively. Suppose we consider a molecular system that has 2 electrons to fill its 2 energy levels. The highest occupied MO, the HOMO, and the lowest unoccupied MO, the LUMO. Then we can have a singlet state in which the HOMO is doubly occupied, or a triplet state in which the HOMO and LUMO are each singly occupied with the same spin. Since in an extended Huckel calculation, the total energy of a system is given by the sum of the energies of its occupied orbitals, the singlet state in such situations will always be more stable than the triplet state. And this can sometimes be in disagreement with experiment. However, it is also true that we can get indications in an extended Huckel calculation when such errors are probable. How? As electron-electron repulsion makes the double occupancy of an orbital energetically unfavorable, the triplet state will become more favorable than the singlet state if the HOMO-LUMO energy gap is small. So, if one finds in an extended Huckel calculation for a molecule a small HOMO-LUMO gap, one should be extra careful about concluding whether the singlet or the triplet state will be the actual ground state. On the other hand, that extended Huckel calculations do not depend on the number of electrons in a system leads to definite advantages that are not available from first principle quantum chemical theories. Since extended Huckel calculations can be simply set up and run fast, they can be used to study large molecular systems and extended solids which contain so many atoms that high-level quantum chemical calculations are impossible or difficult to perform on them. Now suppose we have a composite system AB. It is easy to express the orbitals of this composite system in an extended Huckel calculation in terms of the orbitals of its constituent fragments A and B, even in the case when the fragments are functional groups. In the case the geometry of the fragments remains the same, the orbitals of the fragments are transferable from one molecule to another, and this fragment molecular orbital analysis is a very useful tool in extended Huckel calculations. It is interesting to go through some of the applications of the extended Huckel method in biophysics. The first such application was done by Hoffman himself. In 1969, Hoffman and Imamura published their work on the application of the extended Huckel theory to understand the properties of biomolecules. In that study, they carried out calculations on the conformations of glycyl and alanyl residues and compared the results with classical force field based potential energy surfaces. Subsequently, Rossi et al. In a series of work reported the results of extended Huckel calculations on longer polypeptide chains and the stability of secondary structures. In India, starting from 1970, Professor Girjesh Govil and co-workers explored the conformations of oligo and polypeptides as well as of nucleic acid constituents in a series of work using the extended Huckel method. Lastly, let us mention a very interesting application of the extended Huckel method in biophysics that have appeared recently. In a very recent work with the title Quantum Criticality at the Origin of Life, which appeared in Journal of Physics in 2015, Gabor Vatte and co-workers have explored the proposition that molecules taking part in biochemical processes from small molecules to proteins are critical quantum mechanically. They argue that electronic Hamiltonians of biomolecules have such properties that the material is neither a metal nor an insulator but a new quantum critical substance. Now, what is quantum criticality? The idea actually comes from solid-state physics. Quantum critical states are described as unusual electronic states that are positioned somewhere in between conduction and insulation so that under specific conditions, the flow of current in the system becomes unpredictable. When such a current flow takes place, the magnitude of the current can fluctuate by several orders. For their numerical studies, they selected enema structures of the solution form of myoglobin and they downloaded it from the protein data bank, and the structure contains the protein data bank ID 1MYF. You can see the structure in the picture. The extended Huckel calculations were carried out by the numerical package that we mentioned previously, and the package is YAE-HMOP. There were 6,329 valence electron atomic orbitals, and the extended Huckel Hamiltonian and overlap matrices were of dimension 6,329 by 6,329. Their calculations showed a fractal nature for the eigenfunctions, confirming their proposition that the system is midway between localization and delocalization. And if confirmed by experiments, this would imply a new mechanism of electron transport across a protein molecule. Now, if we consider the theory of Huckel molecular orbital in the previous modules, we find that the theory neglected the effect of electronic interactions. However, to correspond to reality, the effect of electrostatic repulsion among electrons should be taken into account. Although the extended Huckel theory tries to address this deficiency by parameterization, in many cases the simple parameterization procedure proves to be insufficient. The self-consistent field molecular orbital theory is one way of improving the description by taking into account in more detail the effect of electronic interaction. In the next module, we shall introduce the basic idea of the self-consistent field molecular orbital theory, and the theory will be discussed in greater detail in subsequent modules. So let us briefly summarize the main points we learnt in this module. In this module, we have introduced the extended Huckel theory and showed the basic steps of its theoretical calculations. We have also discussed how the theory is implemented computationally. We have discussed a widely used analysis tool proposed by Mulliken, which can be used to analyze the results obtained from an extended Huckel calculation. We have also discussed applications and shortcomings of the method and the need for more accurate theories such as the self-consistent field molecular orbital approach.